Well, hello, and welcome back to Engineering 211 Statics, and this is going to be the final lecture that we have this term. I want to talk about area moment of inertia. This is not something that's necessarily going to be on the final, but something that's going to be an important spring term when we do strengths and material. So I want to start talking about it now, give you a chance to think about it, and if you relate it to things that you see in math and things like that. But you should expect problems like you've seen out of Chapter 9, center of area, center of volume, center of mass, those types of problems. But I would not expect a area moment of inertia problem on the exam. So if you wanted to wait and look at this lecture over vacation or something, that'd probably be fine for you. Well, I wanted to start this discussion and think about if you had some pressure distribution here. Okay, and if I look at this area, and we're going to say that this pressure distribution is triangular. This might be a little bit like you'd have if you had some water pressure at the top. It's less pressure. As you go deeper and deeper, the pressure gets greater and greater. So if I look at this arrangement, this triangular pressure distribution, and I look at this area, dA, located some distance down from where the pressure is equal to 0, this line that we're going to call AB, that's some distance y down. I can talk about the force on dA, and say that that's proportional to, that's the symbol that I've used for that before, the force on dA is proportional to y, the distance y, times dA. Okay, and because the pressure is going to get larger as a function of y, and then you multiply the pressure times the area, and you're going to get the force, right? We have that force is equal to, if we take force and we divide it by area, that's equal to pressure, right? Okay, so force divided by area, and the units even work out that way. If we were to take pounds over square inches, PSI, that would be pressure. So we can see that the force is proportional to the area times the pressure, where the pressure is a function of y. Now, if I want to talk about the moment, about the line, let's say AB, okay, well, that's going to be proportional to y times then the force, right? So we're going to have y times y dA. Or if I talked about the total moment, that would be just for the differential element, the moment about AB for, we could say, for dA. If I talk about the total moment, I could say that this is proportional to the integral of, just summing them up. What do I have? I have y squared dA, don't I? And having this integral of y squared dA, that brings us to a new term. We can say that the moment of inertia is defined as the integral of y squared dA. Now, you may have seen this before in math. They may have called this the second moment of area. It's going to be Strengths and Materials, Engineering 213, before we talk about the first moment of area, but this is the second moment of area. And let me quantify this a little better, and then we'll talk in general what it is and how it probably differs from what you maybe have talked about this term in physics. So if I look at an x-axis or a y-axis, and I look at some body here, and we talk about then this element dA, I can talk about some y distance here. I could talk about some x distance here. And I could even talk about some r distance if I wanted to, like that. So I could say I about x is going to be equal to the integral of y squared dA, that I about y is equal to the integral of x squared dA, and we could even talk about I about z, which would be the integral of r squared dA. And since, this one's probably worth maybe talking a little more about, since x squared plus y squared would equal r squared, we can talk about I about z being equal to ix plus iy, which sometimes we'll call j, or this whole thing will be known as the polar moment of inertia. The polar moment. Okay. For our work, we're just going to keep track of these. Now, if we look at the units on this, the units on all of these, the units would be length to the fourth power, right? Because you have length squared, and then area is going to be length squared, so you have length to the fourth power. So you might have inches to the fourth, or feet to the fourth, or millimeters to the fourth, or meters to the fourth would be some possibilities. And that might bring up some concern, because I suspect that you have maybe talked about a moment of inertia in physics, and it hasn't had those same units. So let's compare and contrast, tie this to how it's the same, how it's different from mass moment of inertia. Mass moment of inertia, you usually would have the integral of some distance squared times some mass, right? dm, essentially, integral of x squared dm, something like that, and it ended up with units of what? Distance squared. So let's see, we'd say length squared times mass. So you might have kilogram meters squared would be a common one, something like that. What this really tells us is how the mass is distributed about some axes. So let's say that we have two flywheels. We have a flywheel that maybe looks like this. Okay, and it's rotating about this point like this. And if we were to take a side view of this thing, if we were to look at the side of that, maybe it's very thick. Okay. So it's rotating about that axis there. Or what if we had something like this, where we had a flywheel that was much larger like this, and it was again rotating like that. And if I viewed it from this direction, I had something that was like that. Okay. Well, if I look, and a lot of times this is an integral of r squared dm or something like that. It's again distance squared times mass. And we could talk about, these might have the same mass, this might have the same mass, but what about the mass moment of inertia for this? I, in this case, is going to be much larger than I in that case. While they have the same mass, the mass moment of inertia is going to be much larger, because if we look at a piece of mass here, it's much closer to this centroidal axis than a piece of mass there. Okay, so what this does is really gives you a measure of how your mass is distributed. So if we compare that to area moment of inertia, area moment of inertia, where we have the integral of, let's say, distance squared dA. So we're going to have units like, and if I wanted to stick with the metric, it'd be meters squared, or we might have inches squared or feet squared. And what we're saying here is, if we look at the cross-section of a beam, so maybe we've taken something that's loaded and bending, excuse me. We've got a moment here, we've got a distributed load here, maybe even a concentrated load, and I take a section and I look at this, okay? And I have some possibilities for this. I might have a section that looks like this, or maybe I could take that same mass, that same area, and I could distribute it differently. Maybe I could put some of it up here and then connect with a thin piece like this, and then do something like this. And why these two might have the same mass, their mass moment of inertia, the area moment of inertia, the area moment of inertia, I, for this one, is going to be much larger. Okay? The moment of inertia for this one will be much larger, because if I look at an area element here, most of the area of this one is way out there, that this number here gets larger. Just like on our flywheel example over here, if I looked at this distance here, I get to square a larger number than on that one. So what the mass moment of inertia does is gives you a distribution of how the mass is distributed with respect to some axes, and the area moment of inertia gives you a distribution of how the area is distributed with respect to some axes. Okay. Now, a lot of times people will just talk about moment of inertia. Okay, they'll come along, talk about moment of inertia. They'll come along, talk about moment of inertia. Well, how do you figure it out? Well, one good way is the units. If it's distance, and I haven't got this right here, it's distance to the fourth, isn't it? Distance to the fourth. So if I'm looking at meters to the fourth, or millimeters to the fourth, or feet to the fourth, or inches to the fourth, I know that I have area moment of inertia. Okay. If, however, I have some mass term, I'm not going to get sidetracked with slugs and whatnot, but if I have some mass term here, let's say kilograms, we'll keep it really easy, times distance squared, then I know I have a mass moment of inertia. Okay, so when someone, and we do this a lot, we talk about the moment of inertia, and we don't necessarily say it's a mass moment or an area moment. You're going to have to sort that out with the units in the context of what you're in. If you're in a physics problem, if you're in a dynamics problem, if you're looking at something rotating, you're probably looking at this. If you're in a strengths and materials problem or a statics problem, you're looking at a beam or something like that, you're probably with this. Okay, so hopefully that gives you a little bit of idea, compares that to things that you may have already heard or been talking about. Another thing that you've probably heard is the parallel axes theorem, and there's certainly a parallel axes theorem for this. So let's say that I have a body here, and it has a mass center. Okay. And I've got some axes out of this. So we'll say that this is, why don't we say this is x naught and y naught. And then I'm going to look at some coordinate system here, x and y. And I can say that I about x would be equal to I about x naught plus the area of this thing times the distance. We'll call this, why don't we call this dx squared. And likewise, I could say that I about y would be equal to I about the y naught plus the area times, let's say, dy squared. We'll say that this is dy. Okay? And the big thing about this is this has to be through the mass center. And I probably shouldn't have necessarily said the mass center, but the centroid must be through the centroid. Okay? So let's say that we had some axes up here. Could I convert from this axis directly down to here? No, I couldn't. I'd have to convert from this axis to the mass, to the centroid axis here, and then again, so I'd have to go from there to there, and then from there to there. Okay, so it's very important that these are through the centroid. Okay, through the centroid when you use the parallel axes there. The units on this hopefully work. You're going to have distance to the fourth here. So let's say inches to the fourth, and what would you have? You'd have inches squared in the area, and then if this is in inches, you'd have another inches squared, so inches to the fourth. So the units are going to work out on that. Now, if we go back to physics, what did you have for your parallel axis theorem there? You probably had I about x is equal to I through the mass center on that thing, plus the mass times the distance squared, right? Instead of the area, you had the mass term there. So very similar expression. Again, just shifting this, the parallel axes theorem. Okay, the parallel axes theorem. Well, let me try a problem. And maybe before we do that, let me go back and look. Oh, I'll just use a separate sheet here. If, like we said, if we have a well, no, I'm going to go ahead and do some calculations first. A really common arrangement that we have is when we try and find the area moment of inertia of a rectangle like this. Okay, and we've got the centroid, of course, here. We're going to say that this is, let's say this is x, and maybe we'll say that we'll call this x naught, and why don't we call this axis here just x. So this is the x naught through the centroid. And I'm going to say that this distance is h over 2, whereas this distance is h over 2. So our cross-section has a height of h. And then I will say that this distance here is the base divided by 2, and this is the base divided by 2. So it's base times height is the cross-section on this thing. And we'd like to find I about x naught, and we'd like to find I about x. So I can say that I about x naught would be equal to the integral of y squared dA, right? So we can say that this is equal to the integral. I'm doing it about this axis, so I have to go from minus h over 2 to h over 2, right? And then I'm going to have y squared, because my differential element is going to be up here like this. There's my differential element. I have y, so I'm going to have y squared times, what's dA? Well, dA happens to be the area of this differential element, which is going to be the base dimension, b, times, what's this tiny dimension there? dy, isn't it? So I'm going to say that this is b times dy. So I'll have b times dy. So you can actually go through this. This ends up being what? Base times y cubed divided by 3, evaluated at minus h over 2 and h over 2, which gives me what? Base times height cubed divided by 24 plus base times height cubed over 24. Is that right? Because when I cube a negative, I get the negative back, and then I'm subtracting the lower limit, so the negatives cancel. So this is from a minus minus. So it gives me base times height cubed divided by 12. So that's I about x naught. That's through the centroid. And that's actually an important one. We tend to use that one a lot. Base times height cubed over 12. Now, there's another way that we could get I about x. We get it two different ways. We could say that I about x is equal to exactly the same thing here, except we're going to say what? Well, we're going to go the integral from 0 to h of, let's see, looking at the wrong spot here. I'm going to do exactly the same thing that I did up here. So this is y squared times b times dy, but this time instead of going from minus h over 2 to h over 2, I'm doing it about this axis, so I'm going from 0, h is equal to 0, to y is equal to 0 here, up to y is equal to h. Okay, so when you do this, you're going to come up with what? Base times y cubed over 3 evaluated at 0 and h. What did we end up with there? Base times height cubed divided by 12. Is that right? I haven't done that right. Let's say base, then height cubed divided by, whoops, I just don't want the 12. I just have plain old base times height cubed over 3, right? Because I put that in there. Yeah, I'm going to have 3. Okay. Could I try this differently? I could say, and we don't use this one near as much. When we look at a beam and bending like the problem that I posed back here, when we look at this arrangement, we're interested in I about this centroidal axis. Okay, so this one we don't use quite as much. But could we get this another way? Well, we could say that it was equal to what? This Ix would be equal to Ix naught plus what? Plus the area times the distance squared. So I'm going to take this base times height cubed over 12, and I'm going to add to the area, which is base times height, and then the distance, what's the distance? That's h over 2 squared, so I have h squared over 4, right? So there's my area times my distance squared, so this is equal to base times height cubed over 12 plus base times height cubed divided by 4. Let's see, this is then 12, and I have 3 of those. So 4/12 is 1/3 base times height cubed, right? Is that right? 4 goes into 12 3 times, so 3 and 1 is 4. So 4/12, yes, 4/12 is 1/3 base times height cubed. So we get the same answer, and you can see the power of the parallel axis theorem, and also the importance of making sure the limits of your integral are right. This is probably the answer that we use quite a bit more often. Well, speaking of that, let me try a numerical example then. So let's say that we have a 2x12, and we're going to arrange it this way, or we're going to arrange it this way. Okay? And again, I'm going to say that I is equal to base times height cubed over 12. So here my base is 1.5, and the height is going to be what? For a 2x12, it's 1.5 inches by 11 1/4. And now over here I have a base that's 11 1/4 and a height that is 1.5, right? So I'm going to say that I have base 1.5 times 11.25 cubed divided by 12. And here I'm going to do exactly the same thing, but I've got to change my numbers. I'm going to say that I is equal to, the base is 11.25 and the height is 1.5 that I get to cube, and then divide by 12. So this one turns out to be, should be about 178, I think. That's a number I used to use a lot. Yeah, 177.9, 178. inches to the fourth. Whereas this one should be about 3 or something like that. Yeah, 3.2. That should be about right. That's 1.5 cubed. Yeah. 3.2 inches to the fourth. So the I for this one is much, much larger than I for that one, which is going to be important when we get to spring term. We start doing design. This is going to be a lot stiffer and a lot stronger than this arrangement. Okay, and you can start to see that in other things. If we look at this is essentially a 2x10, and here is a I joist. We've got these two. This is an engineered product. This is saw lumber. This is an old piece of lumber because the grain's very nice and close together. But if you look at these, and you've got some in the display cases outside the lecture rooms and whatnot, but this one, what we've done is we've taken away this material here. This material here is located excuse me, rather close to the centroidal axis. And if I look at my centroidal axis here and I look at this material right here, it doesn't contribute a lot because it's located very close to that axis. Whereas the material out here does a great deal because this distance that I get to square is going to be a much larger number. So what we do with this is we take the material away from here where it doesn't do a lot of good, and we concentrate it out here. Now, these are about the same height, but so this one is going to be weaker than this one, but pound per pound, this is going to be a lot stronger because it's a lot more efficient cross-section. And if we allow this to be slightly taller, we'd probably get something that is as strong or stronger than this piece. So some things to think about when you're doing that. When you start looking at the area moment of inertia, a section like this is a very efficient section. Well, the last thing that I want to talk about with this is radius of gyration. So you've got some notes if you want to continue on and work problems like this and get practice. If you go to the website, there's a subpage in the 211 folder that has notes, and you've got some section notes in there, so you can get some practice on this if you want. I'm going to finish up with a final concept. And again, I mentioned this was not on the final, so if this stresses you out, don't worry about it. But we'll see this again in statics. I mean, not statics, but in dynamics and certainly in strengths. And it's the concept of radius of gyration. Radius of gyration, if you could imagine that you have some body here that has some area, and we have then some reference, and we talk about, if we wanted to talk about the area moment of inertia about this reference here, we could talk about the radius of gyration. And what the radius of gyration does is that if you take this area and you make this infinitesimally thin, so that's 0, and then this is going to have to go out to positive infinity, and this is going to have to go to minus infinity. So you concentrate this area on a line that's going from positive to negative infinity. This distance here is the radius of gyration, k. Okay, is the radius of gyration k. So we could talk about k, x would be equal to the square root of ix over a, or ky would be equal to the square root of iy over a. Essentially what this tells you is if you have this body some distance from your reference, the radius of gyration is the distance from your reference that you could concentrate this area in an infinitesimally thin line and have the same area moment of inertia. Now you can also do this with mass moment of inertia. You're just going to take I and divide by the mass, and instead of distributing the area on this, you're going to distribute the mass like this. Now if we look at the units on this, If you take I, which is going to be in distance, let's say inches to the fourth for sake of argument, and I divide by the area, which is inches squared, and then I take the square root of that, what do we have? We're going to have the square root of inches squared, which would be inches, right? So indeed, this is a distance. Okay, and it's the distance that you could concentrate this area on that line. Or if you're talking about the radius of gyration for a mass moment of inertia, like we'll do in dynamics, it would be where you would concentrate the mass. So occasionally you'll hear someone talk about the radius of gyration. If they tell you the radius of gyration and they tell you the area, what they're really telling you is the area moment of inertia. So don't let that throw you. If you're a person that likes to think about distributing area or mass along this line that's infinitesimally thin and going from positive infinity to minus infinity, if you like thinking about that, this is great. If you don't like thinking about it, well, just remember these equations and you can convert that radius of gyration back to a moment of inertia. Well, I think that was really all that I wanted to talk about. You do have some homework problems you're going to need to get through on this, but I think you'll be able to do that. Like I said, you shouldn't see any of this on the final, but you will see it definitely spring term, so make sure that you are prepared for that. I guess with that, we get to the last page. We get to the end, so I'll make sure that everyone's aware that it's the end. So hopefully with this entire term has been a good foundation in the study of mechanics, given you some things to think about, some practice, made it so that you can analyze systems with free body diagrams or shear and moment diagrams way better than you could when you started. If that's the case, we've probably done things well in here. Remember that you need to finish up your homework and turn that in at the final, and you also need to make sure that you take a final. So figure out where the final is and what time it is, and make sure that you show up for that. So I'll see you at the final, but until then, take care and thank you for watching.